Hello and welcome to my presentation, which is prepared by me and my consult from Istanbul Technical University, Professor Dr. Cengiz Hacıyev. And now I'm going to begin my presentation. Thank you. Let me share the screen with you. Our study, which is devoted to adaptive Kalman filter based sensor fault detection, isolation, and accommodation applied to Boeing 747 aircraft. And here is the outline. You can see our plan for this presentation. I'm going to start with the motivation part. Recently, the research in aerospace and aeronautics pay very enormous attention to sensor faults, detection, isolation, and accommodation for having flight safety. And our approach has an innovative side for enhancing the accuracy of the sensor state values after the fault, and the method which is implemented makes it possible to get away from the vital casualties on behalf of flight safety of the aircraft, beyond the safety of the aircraft. Our methods, we have a civil aircraft transportation, Boeing 747 4-engine wide body, and it has an operating point of conditions which is 35 feet altitude and 0.85 Mach speed, which is approximately 970 kilometers per hour, and 10.5 kilometers altitude. Our nonlinear Boeing 747 flight model for aircraft model is linearized around this operating point, and via MATLAB Simulink program software, the state space representation of the lateral flight dynamics are gathered as shown on the down. Here, A is the system transfer matrix, transition matrix, B is control matrix, C is output matrix. We used Kalman filter for the estimation of the lateral states. Why we do that? Because when we lose a sensor or sensor value, the system estimates the absent sensor value with the remaining with a calculation of the remaining by using the remaining sensor values, and it's come up with an estimation value. Here you can see the Kalman filter algorithm states formulas right down there. Xk is the estimation value, Pk is the estimation covariance value. Here K is the Kalman filter gain. It will adjust itself by related to measurement covariance matrix and the estimation covariance matrix. If the system has more measurement covariance matrix, K will diminish the value of K. Our Kalman filter will rely on more process than the estimation values because the measurements are faulty. Here you can see the delta key is the innovation value. It is the difference between our measurement output and the estimation of the state. Here, capital X K plus 1 is the estimated estimate of the observer. It is different from it is done by the taking the state, taking the state, oh God, am I recording? I don't know if I'm recording. Okay, it's recording. Okay. Check again. Yeah, okay. And here, this is the updated estimate of the observer, and also the covariance matrix is updated with related to the alteration of the Kalman filter gain and the previous error covariance matrix. The fault detection is done to detect there's a malfunction of the there's malfunction on the sensor or sensors. It is done by the statistical test detection, fault detection. It has two hypotheses. H0 there means there's no fault on the system. H1 sensor fault occurs on the system. In our study, fault is implemented in the implied at time period t equals 400 to 600 seconds. And on the graph, you can see the Kalman filter, the measurements are malfunctioned, and also our optimal linear Kalman filter is don't give the right values, which is beta real with the blue one, and you can see the error degree, which is approximately 3 degrees for the estimation Kalman filter you see here, but the measurement error is approximately 8 radians, 8.5 radians degrees, I'm sorry. Okay, after fault detection, this beta k value, we have a function beta k, and it's a statistical. It gets the statistical value of the innovation of the Kalman filter, and you can see the value when a sensor fault is absent. It's not occurs when a sensor fault is when a sensor fault is seen on the system. It affects the mean of the innovation sequence of Kalman filter by changing its value. Therefore, this statistical function gets not exceptional values, extraordinary values. Here you can see the innovation sequence calculation formula. And this statistical function has a chi-square distribution with S degree of freedom. Here S is the dimension of the state vector, which is 4 for us. And the level of significance alpha is selected from the span of the formula. Here we took 0.95 and the threshold value is determined from the quantized table of the chi-square distribution. Chi-square distribution quantized table. So in the H1 hypothesis, if it's correct, the statistical value of beta k will have a higher value than the threshold value, and therefore the fault is firmly detected with firmly. You can see on the graph the threshold value is with the it is red one. The threshold is red. It is red, and yeah. Okay, I got it. You see that the statistical function value exceeds the threshold value during the time period 400, time interval 4 to 600. So therefore the fault is detected firmly. After the fault isolation, we have to make, after the fault detection, we have to manage which sensor is faulty. We know there's a fault in the system, but we don't know which sensor is faulty. Therefore, we have to isolate the fault, isolate the sensor, which is which sensor is the faulty one. We make it by, we succeeded by implementing an fault isolation algorithm. It takes the Kalman filter innovation value of the sensors one by one, and it gets the difference from the mean of all of the sensor Kalman filter innovation values. Therefore, if there is a change, various enormous change in the filter, this value, we can see the fault is isolated. Here M is the width of the sliding window. We took the M here 1. It's like 2. It's like 2. Okay. Therefore, yes. All right. And you can see on the right side, you can see the first one is for side slip angle, Kalman filter innovation SK value, and the second from top is yaw rate, third one is roll rate, and last one is roll angle. These are the normalized innovations of the optimal linear Kalman filter for measuring lateral measurement channels. In case of just one side slip angle sensor fault, and All right, now we have now that we have isolated the first stage, we have detected the fault. Second stage, we have isolated, and the last stage is accommodation of the fault. Kind of remedy of the fault. Let me check. Remedy. Am I saying it correct?
Remedy.
Remedy.
Remedy. Remedy. Remedy.
The first, second, and third, we have to. Third one is that we have to. We have a fault accommodation stage which estimates the states and remedy the sensor values. Remedy the sensor values. Sensor values. We have done this by applying an adaptive Kalman filter. This filter takes kind of, there's a scale factor. It's do its job by distinguishing the actual and theoretical values of the covariance of the innovation sequence. And this filter is used to get a much better performance and accurate estimation values when fault appears at measurement channels without influencing the past fine characteristics. It aims to correct only the correlated parts, not the old parts of the measurement noise covariance, and eventually the Kalman gain scale factor can be designated through the formula below. And by this way, our Kalman gain here, capital lambda k star takes the diagonal of the lambdas. Here lambdas take the, if our diagonal matrix of lambda k matrix, capital lambda k matrix, it looks for the diagonals of the lambda k, and it takes, if any element of the matrix is bigger than 1, it makes it 1. Therefore, by this way, the measurement fault, the fault measurement is diminished. The effect is diminished, kind of diminished. Here, the regulated lambda k is then lambda k star is then used to establish the capital lambda k star, and in our Kalman filter gain k is re-established by multiplying the lambda k star with the measurement noise covariance matrix Rk. In case of any malfunction, the correlated element value of the scale matrix raises. Therefore, a smaller Kalman gain here on the K, on the K. No. And Kalman gain is found to be smaller, which reduces the effect of the innovation on the state estimation process. Now, our first case is, our first fault case is side slip angle fault. And you can see the Kalman filter, adaptive Kalman filter applied in case of side slip angle fault. You can see the yellow oscillation malfunctioned value is for side slip angle measurement, and the red one is the result of the adaptive Kalman filter. The Kalman filter is adapted to the fault, and it's estimated the values which are closer to the real values, and the fault is accommodated by this way, and it's a good remedy method for sensor faults. Here you can see the error is reduced on the middle graph, and the last graph illustrates the error variance during the iterations. Our error variance is take bigger values during the fault stage, which is kind of, it's not natural. Okay. In case of double sensor faults, the faulty sensors are, we have two faults here, which first one is roll rate fault, and the last one is, second one is, and the following one is roll angle fault, sensor fault. And you can see, even if there's a fault on the time period, the adaptive Kalman filter makes it possible to estimate fine values. And here you see that in roll angle, measurement channels are faulty. The fault type is measurement noise increment fault, and the Kalman filter estimates very good results. Broken sensor values are corrected by the algorithm. And now we have first detected the fault, isolated it, and have a good remedy. And the last stage, how accurate is our remedy for the repaired sense or the enhanced sensor values, estimation values are how good. We can differentiate it. We can see the difference by using the root mean square error, and the root mean square error values are better if the value is closer to 0. And you can see in case the table 1 demonstrates in case of the first fault, which was a side slip angle sensor fault, we have to look for the remaining sensor fault, remaining sensor estimation values, with the, if we compare the all optimal linear Kalman filter root mean square error value with the adaptive Kalman filter 1, for the remaining sensor values, The adaptive ones are closer to 0, therefore it's, and in table 2, in case of double sensor faults on roll rate and roll angle, again our adaptive Kalman filter shows better results because the root mean square error value is closer to the 0 compared by the optimal linear Kalman filter. And therefore, it shows our algorithm performs well. Thank you for listening to me. And if you have questions I can answer, thank you. See you next time. And thank you for listening to me. It was a good pleasure to meet you. It was a pleasure to meet you. I appreciate you for you all. See you on the next one. And see you on the next one. And see you, and I hope to see you on the next one. Thank you. Thank you for listening to me. I appreciate to have a role on the symposium. And I want to thank you all and to my professor. And maybe next time, see you on the next one. Thank you for listening again. See you on the next one.